Okay, the next set of notes in this unit is about wave behaviors. These are examples of things that waves do, and what they do is kind of common among all types of waves, including mechanical and electromagnetic. The first thing we're going to discuss is about how waves interfere. Interference means when two waves meet each other, and they meet at the same place at the same time, we call that interference. And a few different things can happen depending on how the waves hit each other. One thing that can happen is called constructive interference. Constructive interference means two waves are going to meet, but they do it in a certain way. Now look at this diagram here, and what you see is that there's a crest here and a crest here. So these two waves, they look identical. These two waves are identical, but when they meet and there's a crest lined up with another crest, if they do that, we get something called constructive interference. Here the amplitude is 2 blocks up, and here it's also 2 blocks up. So both of those are 2, it would add up to make 4, and that's what you get over here with the new wave. So two smaller waves add up to make a bigger wave. That's what this is really trying to show. 2 and 2 makes 4, and this one is 4 blocks up. So that's constructive interference. It only happens when the waves have crests and crests lined up. Trough and trough are lined up. Okay, so amplitudes get added together, and we call that constructive interference, also reinforcement or in phase. A good example of when you might notice this is, suppose these were two sound waves that were coming from a speaker, sounds coming out of a speaker. Well, you would hear one sound, but if you hear a second sound coming out of a second speaker, it's going to sound louder. It could sound louder. Well, that's constructive interference, where the two sound waves build each other so that they build each other and become a louder sound. All right, the second kind is destructive interference. And it's similar, but this time we have a crest here and a trough here. This crest is 2 high, and this trough is still 2, but it's down 2. So in that case, when the amplitudes get added together, what do you get on this side over here is a straight line with no amplitude. The amplitude is 0 here. So this would be like if you had a sound and maybe like two tuning forks or two sounds produced that cancel each other out. So it only happens if you can get a crest and a trough to line up, like in this drawing. This is the newer iPhones, and I think some Android phones do have noise cancellation technology, where it's supposed to make the calls clear because sound waves from noise are canceled out, and so that when you're listening on the phone, when you're having a conversation on the phone, you only hear what comes out of the speaker and not the noise around you. And it uses this behavior of waves, destructive interference. This is sort of in between, but in between constructive and destructive. This is a phenomenon you would notice when you had two tuning forks or two things producing a sound that were slightly different. Two tones of slightly different frequencies, like 100 hertz and 120 hertz. If you ring them at the same time, you hear beats. Now beats are, this is what happens, a crest here in these two waves, a crest and another crest, they line up, so we expect to get constructive interference, or we hear the sound being louder. But later we have a trough here and a crest here. So when a crest and a trough line up, we get destructive interference and the sound gets quieter. And that pattern gets repeated over and over again here. Loud, quiet, loud, quiet, loud. And so what we hear is the volume going up and down. And as it goes up and down, it does it with a regular frequency. We call that beats. So there's a beat frequency of the volume going up and down. It turns out that the beat frequency is also equal to the difference between the two original tones. So 100 hertz tuning fork and 120, if you subtract, you get 20. The beat frequency of this wave would be 20 hertz. Resonance so it turns out that anything that vibrates or oscillates has what we call a natural frequency that it vibrates. And a tuning fork is a good example. When you ring a tuning fork, like for example this one is the note C, you can't ring this tuning fork and make it a different note. It has to be a C because its natural frequency produces the C. So let's suppose you had two of these tuning forks that were identical. Resonance only works when the two frequencies match, their natural frequencies match. And so it says the frequency of a forced vibration on an object matches the natural frequency. So if you could ring this tuning fork and cause it to vibrate and bring it near another tuning fork, this one would start to vibrate. That's what resonance is. The word resonance means re is like again, sonance, sound. Sound again. If you ring this one will start to ring also. That's what resonance is. This is the phenomenon we see when, like if you've ever seen a video or something of an opera singer who sings a really high pitch and they can break glass, their frequency of the sound that they sing, if it's loud enough, can and at the right frequency, it can match the natural frequency of a wine glass and force it to start vibrating maybe so much that it breaks. That's resonance too. This analogy is showing the same thing. This is a person pushing a swing, and as the person pushes, they have to push with the right frequency to match the frequency of the swing. As a swing goes back and forth, it has a natural frequency, and this person, as they push it, they're going to match that natural frequency. Every time the tire comes to him, he's going to push it, and he's going to force it to vibrate in the same frequency so that they're resonant, they're matching. It only would work if they're two frequencies matched, similar to these two tuning forks. Okay, Doppler effect. I have a video here that shows an example of Doppler effect. Just back it up. Okay, so that was a fire truck that had a siren going, and what we observed is the fire truck moved towards you, and then moved away from you. As it was moving towards you, we hear the pitch higher, and as it moved away from you, you hear the pitch lower. The frequency appears to change because it's moving towards you or moving away from you. That's Doppler effect. When the observer or the source of the sound are moving relative to one another, that's Doppler effect. We hear a change in the frequency. And how we explain it is, as the fire truck was moving towards you, the sound wave gets compressed, and we hear it as a higher pitch. It's almost like the waves are closer together, so they're a higher frequency. And as it's moving away from you, we say it's stretched. The waves appear farther apart, so it's a lower frequency. We would notice this anytime it's a police siren or maybe even a train approaching you, but if there's a relative motion between the source and the observer of the sound, you can hear the Doppler effect. Alright, next few slides we're going to talk about a few things that waves do as they change direction. So mostly here, reflection, refraction, and diffraction are the way that waves change direction as they hit a boundary or a different material, a different medium. So a medium is what the wave is passing through, but if a wave goes from one medium to another, it can, if it interacts with a medium, it can change direction, and it happens for different reasons. But you know, a sound wave going from air into water, or any wave going from air to water, is going to change direction, and that's what we're going to talk about in the next few slides. Reflection is when a wave hits a surface or hits a different medium and then bounces off, hits a boundary and then bounces off. So we normally talk about this with light, but it can happen with anything. When you look at a mirror, you're looking at light rays that bounce off the mirror, but sound waves do that. There's echoes. So essentially in this drawing we see there's an incident ray, which just means a ray that is about to hit the mirror. And it's hitting it at an angle, and what it's going to do when it hits the mirror is bounce off. Well, that ray we call the incident ray coming into the mirror, and then after it hits we call it the reflected ray. There's an imaginary line that's perpendicular to the mirror. This is a perpendicular normal line, that's what that's called. The incident ray has a certain angle that it is away from that normal line, and that's supposed to be the Greek letter theta, which stands for the angle, the number of degrees. So if this were 30 degrees on this side, the incident ray was 30 degrees from the normal, then as it reflected, it would also be a 30-degree angle away from the normal on the other side. That's called the law of reflection, that these two angles would be the same. The incident angle and the reflected angle would be the same. So that's reflection. The wave changes direction because it hits a boundary. Well, suppose that a wave hit a boundary but could pass through it. That's what happens with refraction. Refraction, we see, oh, this light or this wave is hitting this boundary, but it's not going to reflect off it. It's going to pass through it because it's transparent. We mostly talk about this with light waves because we can see, obviously, light can travel through air, and suppose this is water, light can travel through water. Well, as a wave passes from one medium into another medium, it changes speed because the speed depends on the medium, and if the medium changes, the speed changes. If the speed changes, the direction will change. And that's what this drawing is showing. This is light going through air. As it hits water, it actually slows down a little bit. And as it slows down, it changes direction and bends kind of a little bit more downward. The angle on this side is a lot smaller. The angle on this side is bigger than the angle on that side. That's refraction. It slows down and causes a change in direction because it changes medium and changes speed. And you probably have seen pictures like this before, but this is refraction. A pencil sitting in the water, this part of it is sitting out of the water and this part is underwater, so you see it and it looks like it's bent. Well, it's really because the light rays have changed direction as they come out of the water, but it's because they're changing from one medium into another, from water into air. The index of refraction is just a certain number that every material, that if light passes through air, it has a certain index of refraction. It has a different index of refraction for light passing into water. Okay, the last thing is about diffraction. And diffraction is, you don't really notice this very much, but there are a few examples I can show you here. Diffraction is when a wave changes direction or spreads out, and that's because it moves through an opening or around some object. And so, look at this picture here. What you can see, this is supposed to be these lines, these vertical lines here. It's like you're looking on above it, at like a bird's eye view. You're looking down on it, and those are the crests of the waves. And so the crests of the waves, they're passing through an opening. There's a small opening here, but what happens on the other side as it passes through the opening is that you can see the waves have changed directions, and they're going all directions now. Some of the waves are continuing the same direction, but over here it's like they're going that way or that way. And bounced off of anything. They change direction because they're passing through a small opening. So this picture down here is an aerial photo of water waves that are moving towards the shore, but as they do, they're going to pass through these two rocks, these two small islands or rocks there, and you can see what happens. It's kind of hard to tell what direction the waves are moving, but they're moving towards the ocean, towards the land. But look what happens when they pass through the opening. It almost looks like they form these little half circles here. Well, that's because as they're moving through the water, it's a small opening. As they move through these two rocks, it's a small opening. They change directions, and they go in all directions, sort of like in this drawing up here, or this picture up here. So diffraction might be hard to see in everyday life, but there are some examples that are real things you can show that demonstrate diffraction. Another one that we'll show you in a lab someday is a laser shine through a certain kind of material that is made of really small windows or small openings, and as it passes through, the light rays spread out. That's also diffraction. So you had these three types: reflection, refraction, and diffraction. They are all waves changing directions, but they happen for different reasons. In reflection, it's because they hit a boundary and bounce off, so they change direction. In reflection, they hit a boundary and pass through it, but they slow down or speed up. If they change speed, it causes the waves to change direction. That's refraction. And then diffraction is when a wave changes direction or it spreads out because it passes through a small opening or around a small object.